So when I was developing videos for this video series on equilibrium, I wanted to do a video on Ka and wanted to do a video on Kb. But when I started making the video for Kb, it began to click with me. I really felt like I was just recycling what I was saying for Ka, because to me they're the same problem. So you as a student may not see this, and I really don't want to give you a second video on Kb and present it like it's a different problem, because it's not. And that's what I want you to see with this video on Kb, is that you're going to approach it really the same way you approach it with Ka. There's just a few little things that have changed, but there are things you would expect to change if you're working with a base. So if you haven't watched it already, watch the videos on the different types of equilibrium constants, as well as a video on how to work a Ka problem. Our expression for Ka is always going to be our weak acid, reversibly dissociating into H plus and A minus. Now with Kb, there's a little bit of a complication. We have Bronsted and Arrhenius definitions of bases. The Arrhenius definition says it's going to dissociate to give us OH minus, and the Bronsted definition says it's going to accept the hydrogen to give us the base plus hydrogen and OH minus. Now typically when we work with weak bases, we are working with the Bronsted definition, so we're going to stick with that in this video. So we have Kb, we have our parent base, and unlike the acid, we're going to have water in here. This is where our hydrogen donor is going to come from. And we're going to have BH plus AQ plus OH minus AQ. So a distinction here is that when we had our Ka, we didn't have water up front, and we got rid of a hydrogen. Here with the Kb, we have a water up front, and that's where we get our hydrogen from. Now, don't get locked into the trap to thinking that the B has to be neutral. The base can actually be a polyatomic ion like phosphate. So PO4 minus 3 AQ plus H2O liquid goes back and forth to H, PO4 minus 2 AQ plus OH minus AQ. The point is our base gained a hydrogen as it went across. So how do we solve Kb problems? Well, it's more a question about what you're being asked to find, but the approach is still the same. There are three things we're always going to need for solving these types of equilibrium problems. The first is always our equilibrium constant, in this case Kb, equals our expression for Q. And again, this is true if and only if we're at equilibrium conditions. The second thing we need is our expression for Q. Now, when we did our expression for Ka and our Q was H plus times A minus over HA. In this case, it's BH plus, conjugate acid, concentration of hydroxide all over the concentration of the parent base. Third thing we needed was an IC table. And we're going to populate like we did before. We've got our base. Instead of H plus, we've got hydroxide. We've got the conjugate acid. Now with the Ka problems, what you do is you start populating the table with what you know. Same thing's going to be true with any types of these problems. First of all, we're going to assume the hydroxide concentration is 0, that all the hydroxide we're getting is from the weak base we're working with, not from the water. Changes, minus X, X, and X. So our final concentration of hydroxide is our extended reaction. The question is, what does the problem give you? So the problem gives you starting concentrations and wants you to find the hydroxide concentration. You stick your starting concentrations up here. You'll get an expression in terms of extended reaction that you'll plug into your expression for Q, and you'll solve for the extended reaction using the numerical value for Kb. Let's say you're given equilibrium concentrations and you're asked to find the Kb. Equilibrium concentrations will go down this row. You'll use the extensive reactions if you need to figure out what the concentrations of the other species are. Stick in the numerical row now to find your expression for Kb. Let's say you're asked to find starting concentrations. Plug in your equilibrium concentrations, plug in your unknowns for whatever concentration you're trying to solve for, and use your expression for Q to solve for the unknown concentrations. So if you go back to the video on Ka, it's basically solved the same way. The major differences are, one, the reaction's different. You're producing hydroxide, not H+. This is going to change your table. Instead of having H+, you're going to have an OH-. But that's really it. It's the same approach. Set KQ equals to Q, find your expression for Q, and identify what variable you're being asked to find. The only thing that makes the base problems difficult is you can be asked for things like pH and H+ and POH. That's just a matter of manipulating this concentration. If you go through my other videos, you can see how to figure out how to find pH, POH, H+, and OH-, and how they're all connected.